Our last topic in chapter 16 is something that you may have been wondering for a while now, and it's what determines the strength of an acid. You know, at the very beginning of this year, I asked you to memorize the 7 strong acids. And so you memorized them, but we never really talked about, well, why? Why are these 7 strong, meaning they completely dissociate, whereas the other ones don't fully dissociate? And that's really what we're going to be looking at here. Okay, so this is 16.10, and there are numerous factors that affect acid strength. We're mostly thinking about acids as being proton donors in this section, and so we have some things that we always look at. The first statement here says that if the hydrogen ion is bonded in such a way that the bond is polar and the hydrogen is positive, it will be ionizable. So that means if you have hydrogen and a metal, right, that's not an acid because the hydrogen will be more electronegative than the metal. So that means that, if it was going to break up, the hydrogen would keep the electron, not form H+. So that's why there are some compounds where hydrogen really acts more like a nonmetal, like lithium hydride, for example here. Lithium comes first. That's our way of knowing that it is less electronegative than the hydrogen. And we call the hydrogen hydride, IDE, which is what we add to the more electronegative element. So something like lithium hydride, if that is going to dissociate, lithium is going to be positive and the hydrogen would be negative, which means this wouldn't be acidic at all. What we're talking about is where hydrogen is the less electronegative. So that means not hydrogen and carbon. Even though carbon is a nonmetal, hydrogen and carbon have essentially equal electronegativities, and they form nonpolar bonds, and those bonds do not break. So what are we talking about here? We're talking about hydrogen with any of those other nonmetals, oxygen and chlorine and fluorine, all those guys. So there's a couple things that we look at when we look at this. We look at the strength of that bond, the hydrogen and nonmetal bond. If that is a very strong bond, it's not going to easily break. And what we're talking about here, if we're talking about something like, an acid, what happens is that bond breaks. So if that's a very strong bond, it's not going to break. That hydrogen is not going to come off the nonmetal. The other piece of this is the stability of the conjugate base. What is left over and how stable is that? All of these are important, and depending on certain circumstances, some are more important than other. So the first group that we're going to look at are binary acids. Binary acids means it's an acid with hydrogen and just one other element. And you can see from this table here, what's most important here is the strength of the bond. The stronger the bond, the less acidic it will be. So what can make a bond really strong? Well, size is going to make a big difference there. And that's what we see going down a group. That comparing 2 acids in the same group, the stronger acid is the one with the larger nonmetal. One of the things that we learned in first year chemistry was that short bonds are strong bonds and long bonds are weak bonds. And why is, for example, the hydrogen bromide bond weaker and longer than the hydrogen fluoride bond? Well, because hydrogen fluoride is with the fluorine atom that only has electrons in the 2nd energy level, whereas bromine has electrons up to the 4th energy level. And as we get higher up in energy levels, they're further from the nucleus. So because bromine is larger than fluorine, that bond is weaker, and the acid hydrogen bromide is stronger than hydrogen fluoride. So anytime we're going up or down, the difference is in the size, right? Why is hydrogen selenide, that would be the name for this, stronger than hydrogen sulfide? Because selenium is a larger atom. Then if we go to comparing 2 acids in the same period, so that's in a row, the stronger acid is the one with the more electronegative element. The more electronegative element means that it will pull the electron density towards itself, weakening that bond. And so we know fluorine is the most electronegative element. So if we think about hydrogen bonded to fluorine, these two electrons spend most of their time around fluorine, meaning this bond is quite weak, easily broken. It is weaker than the hydrogen-oxygen bond because oxygen is a slightly less electronegative than fluorine. And nitrogen, hydrogen, nitrogen's even less electronegative, and nitrogen and hydrogen actually isn't even an acid, right? It's a weak base. So what I always sort of remember here is that, I know NH3 is a weak base. I've memorized that. I know water can go either way, and I know HF is an acid. So that's how you can sort of easily remember that as you go across, the the acidity increases, and you've memorized hopefully that hydrofluoric acid is the weak acid, but HCl, HBr, and HI are strong acids. So then as you go down, the acid gets stronger. So that's for binary acids. What about other types of acids? Well, another type of acid that we have here are called oxyacids. Oxyacids are the ones made from basically polyatomic ions, right? So, SO4 2- is a very common polyatomic ion sulfate. H2SO4 is one of our strong acids. Here we have H3PO3. This is H2SO4. And so it's interesting to see, where are these hydrogen? In oxyacids, the hydrogen are always off the oxygen, and the other nonmetal is the central atom. And what makes one stronger than another is all about the electronegativity of the central atom. Okay, so sulfur is more electronegative than phosphorus. You know that because you know the trends going across. Therefore, H2SO4 is stronger than H3PO3. And why is that? Because the we're going to talk about that on the next page, but basically the sulfur is electronegative, which means it's going to pull the electrons towards itself. The oxygen will sort of then pull the electrons in the oxygen-hydrogen bond towards itself. That means that this bond is weaker, and sulfuric acid is more likely to lose a hydrogen. You can see that pattern going on here. These are all oxyacids, the three halogens here with oxygen and hydrogen. So HClO, HBrO, HIO. And what happens is, as the electronegativity of that, in this case halogen, increases, the electron density shifts towards that halogen or that nonmetal. So if this is, for example, if this guy here is the chlorine, then since chlorine is really electronegative, the electrons wind up spending more time around that chlorine. Well, oxygen will sort of make up for that by pulling the electrons more towards itself, which makes this bond more polar and means that the electrons spend more time around the oxygen, which means it's more likely for hydrogen to be stripped off there and that hydrogen to be donated to water. And you can see it reflected down here, even in the Kas. Another trend with the oxyacids, so you need to know that if you're looking at them and they all have the same number of oxygen, it's the electronegativity of the central atom that makes a difference. If they are all the same atom, but the difference is in the number of oxygen, the greater number of oxygen, the greater the strength of the acid. And that's one that you should already sort of know, that H2SO4 is strong. HNO3 is strong, but HNO2 is not strong. H2SO3, not strong, right? So why is that? So as you get more oxygens, right, it's very similar explanation to the last one. As you get more oxygens around it, they draw electron density from this bond. So think of this bond right here. The electrons are pulled like closer to all these electronegative elements, right? Oxygen is fairly electronegative. The electron density is being pulled more and more and more away from that hydrogen-oxygen bond. That weakens that bond. That means that it's more likely to break, and that hydrogen is more likely to be acidic, to be grabbed by water, right? And so you know this because you know HClO4 is a strong acid, right? HClO3 is also considered a strong acid in our textbook. AP doesn't consider it a strong acid, but it's right on the line, so they don't usually use that as an example. But this is HClO2. That's weak. Look at its Ka. And this is just HClO. That's much weaker. So the more oxygens, the stronger acid it is. The more electronegative the central element, the stronger acid it is. Those are for the oxy acids. So here we have a couple of practice problems. The first one says, arrange the following substances in order from weakest to strongest acid. So I already know HClO3, right? That's a strong acid. So I'm going to cross out A because that doesn't end with HClO3. And I'm going to cross out D because that doesn't end in HClO3. So then I have to look back at what are the other ones. Well, I know that when we're looking at oxy acids, the electronegativity of the central atom makes a difference. The more electronegative the central atom, the more strong it is. So the fact that this has HClO2 and then HBrO2, that shouldn't work, right? And same thing here with HI. I is the least electronegative of the halogens, so it's got to be B. Right? And this makes sense that ClO is, or chlorine is the most electronegative of the halogens. So they're going to be the two top. And then the one with the more oxygen is the stronger acid. Then we get, here are two hydrogen and iodine. Iodine is the least electronegative of the halogens. So it's all the way down at the end. But again, the one with the least number of oxygen is the least acidic. In each pair, choose the compound that gives the more acidic solution. So HBr and HF, this one's easy. HBr because I've memorized that it's a strong acid. Think about the reason why though. These are binary. So when we're talking about binary acids where the nonmetal is in the same group, it's all about how strong the bond is, and that's determined by how big the atom is. Bromine has more electrons and higher energy levels, which means that that bond is longer, that bond is weaker, and that hydrogen is more likely to be ionized or to be ionizable, to leave. When I'm looking at these guys, these sulfur and phosphorus are in the same row. So it's not the size of the atom that's making the difference, it's the electronegativity of the atom that's making the difference. And sulfur is more electronegative than phosphorus. HNO2 and HNO, these are oxy acids. They have the same nonmetal, nitrogen. So what makes the difference? The more oxygen, the stronger it is. And H2SO3 or H2SeO3. These are oxy acids. They have the same number of oxygen, so what's making the difference is the electronegativity of the central atom. Sulfur is more electronegative than selenium, so H2SO3 is the stronger acid. The next one we have are the carboxylic acids. So anytime you see this, COOH, that is kind of a strange way of writing it, but every time that we write that, we know that that means that C, double bond to an O, single bond to an OH, and then whatever else comes over here. When these are carboxylic acids, so they are acids, this bond can be broken and that hydrogen can go off with water to make H3O+. And the reason why these are effective acids is because we get resonance with what is the conjugate base, right? If I take acetic acid, what is the conjugate base? It's the CH3COO negative, right? And so we know that actually that bond is not a double bond with one atom or a double bond with another atom. It's like 1.5 bonds. How we would have written it last year, 1.5 bonds to each of those oxygen. Resonance is very stable because carboxylic acids have a very stable conjugate base. That's why they're acidic. And then the very last thing just to talk about with acids and bases is that there is another definition of acids and bases. It's no longer on the AP test, but you should probably know that there's such thing as Lewis acids and Lewis bases. And this is just taking the Bronsted-Lowry one step further, that an acid is not a proton donor per se, but flip those both words. The opposite of a proton is an electron, and the opposite of a donor is an acceptor. So something like this, where that boron is a little bit electron deficient, it is stable with just 6 electrons, but it could handle 8. We consider that a Lewis acid. And NH3, which we know as being a Bronsted-Lowry base, is considered a Lewis base because it's an electron donor. And so it can donate its electrons to make what we call a coordinate covalent bond. That's something from last year as well.